Well, hello, AP Physics students. Mr. Carson coming at you here. We got a roller coaster problem here for problem number 13 today. So let's just dive in here and get rolling. Get it rolling? Because it's a roller coaster problem. Okay. So in our roller coaster problem, we are told that we have a loop-de-loop, right? And the radius r of our loop is 7.4 meters. Okay, and the question that is asked is, when you are at the top, what is the minimum speed that the car could be going without the person falling out of the car? Because obviously, if you're designing a roller coaster ride, we would hope, they would be safe and all that type of thing. Okay, so right away, when I see a circle and an object going in a circle, right away I am thinking about centripetal acceleration, right? And as you know, centripetal acceleration is v squared over r, and it's an equation that's on the equation sheet, so must be pretty important. And of course, your book calls it radial acceleration, right? Which kind of makes sense, acceleration along a radius. But centripetal acceleration, radial acceleration, whenever you have an object moving in a circular path, it must be accelerating towards the center. The acceleration towards the center we call centripetal or radial acceleration, and it's equal to v squared over r. Of course, if we wanted to instead of centripetal force, we wanted to talk about centripetal acceleration. Well, centripetal force is mass times centripetal acceleration by Newton's second law, right? Okay, let's start with our free body diagram. And I drew the roller coaster car here at a bunch of different places, okay? And I want you to note here that no matter where the car is along the track, we really only have two forces at play the entire time. We have our weight and our normal force, right? And the normal force, remember, is always perpendicular, and the weight, pardon me, that should be an N, and the weight is straight down, okay? And I'm just kind of drawing these in here, all right? And let's draw this in here. Okay, so this here is my weight, and of course my normal force here would look like this, all right? All right, no matter where I am along this track, all right, in order to be moving and accelerate in a circle, I must be accelerating towards the center. And the key here to this problem is to realize that at the minimum speed here at the top, okay, so at v min, n must equal 0. In other words, if I made, if the normal force just got to be 0 here, all right, that's the minimum speed I could go without falling out of the cart, okay? If I was going really, really fast, I would need a big normal force plus the weight here, right, in order to keep me on track, right? Down here, okay, so that is the key to this problem, okay? And keep in mind that our weight is mg, so really the key to this problem is just realizing, hey, at the top up here, the centripetal force is only being provided by the weight. That is, the normal force is 0, and so the centripetal force is being provided by the weight. So that's the tough part here, is realizing that. Once you do that, the algebra isn't too bad, right? And as a matter of fact, the mass of the car even cancels out here. So we don't even need to know the mass of the car. So we have V min is equal to RG. Of course, this is a squared. And why don't we bring this up here? So we have V min is equal to square root of RG. Sometimes it's good when I get to the end of the problem just to double check my units here. Okay, this should be in meters per second. R is in meters. G is in meters per second squared. So meters times meters per second squared. Square root is meters squared over second squared, which is meters per second. So looks like my problem is on track here. So VMin on track. I made a pun without even knowing it. So R is 7.4 times 9.8. And if I plug that in, I get 8.5 meters per second is the slowest I could go. Slowest I could go without falling out of the car here. All right. All right, nice work, AP Physics students. You know, staying on track, let's get rolling on the problem. You know, I've had students say, Mr. Kirsten, you know, you should get together with other science teachers and put on a performance where all you do is puns. And I said, tell a bunch of puns with other science teachers. Well, that would just be one big play on words. Get it, play on words, because it instead of it'd be a play because you'd have multiple people performing. It was all puns. It'd be about words. But anyway, nice job, AP Physics students. We'll see you in class tomorrow.